Okay, so in this video, I want to talk about the chain rule and something else. So starting from chain rule, what is chain rule? So for example, how should we compute the derivative of sine of let's say x to the fourth? Okay, x fourth. What is its derivative? So to solve this question, we can think of this x to the power 4 as y, okay? So we can write y to be x to the power 4. And then we say that this value is z, okay? So we then z is sine of x to the power 4, which is sine x. And then, although I didn't mention, but the derivative of a variable with the other variable is also denoted by Leibniz rule, by Leibniz notation as dy over dx. So for example, if y is f of x, then f prime of x is also denoted by dy over dx. And it makes sense because it means that the instantaneous rate of change of y over x, right? So this becomes dy over dx, right? It's like the instantaneous change of y divided by instantaneous change of x. And then we cannot just say it's this divided by this, because this will be 0 and this will be 0. This is actually we do it by taking the limit, right? So this is the limit of the quotient, but we still denote it by dy over dx for simplicity, and then it will make the intuition correct. Okay, so what we are asked to find is what is dz over dx, and then one way to do it is basically the only way to do it is to use chain rule. So we can write this as dz over dy times dy over dx, which means we use this y to first evaluate dz over dy and then use it to evaluate dy over dx. And it makes sense because now I made a typo. It should be sine of y. Okay, so because z is sine of y, so this means that dz over dy, which is the derivative of z with respect to y, it should be cos of y. And then also don't forget this term, which is dy over dx. So we know that dy over dx, which is the derivative of x to the power 4 with respect to x, it is 4 times x cubed. So dz over dx should be equal to this, which is cos of y times 4 times x cubed. But what is y? Y is x to the power 4. So this is cos of x to the power 4 times 4 times x cubed, which means this is, we can simplify as 4x cubed times cos of x to the power 4. So this is the power of the chain rule. So in this case, we actually think about this function as a composition of two functions. This is a composition of two differentiable functions. The first one is sine. The second one is something to the power 4, which is, so that's denoted by x to the power 4. So chain rule gives us a method to compute the derivative of composition of two functions, right? It's different from product because product is not like a typical composition, right? Because for a composition, you give a f and then you give it a g, then g composed of f at x, this is g of f of x, right? But then g times f at x is equal to g of x times f of x. So they are quite different, right? They are not the same thing. So that's why the rules must be the same. So for the product, we have the product rule. For the composition, we have the chain rule. And one might ask why it is not called the, let's say, composition rule. I mean, you can call it a composition rule, but if you think about it as a chain rule, then it makes sense because you just think about this x to the power 4 as a variable, and then take it the derivative, then you get cos of this variable, right? And then you look at this variable, you take the derivative of this variable with respect to x. So then you need to multiply it or times 4x cubed. So this gives you the answer. So you don't need to write this all the time. You just understand this pattern. Does that make sense? So let me say that again. So if you want to find the derivative of sine of x fourth, you first consider this as sine of something. So let's write this as sine of something, and then take the derivative. Then you first think about this something as a variable, and then take the derivative with respect to the star. So then this will give you cos of star, but it is not the end. You also need to take the derivative of this star. Okay. So then in this case, this is cos of x to the power 4 times the derivative of x to the power 4. And you know how to compute this, so you're done. So this becomes cos of x to the power 4 times 4 times x cubed. So let's look at some other examples. So first I will give you some examples, and then I will write down the chain rule. Okay. So what about e to the power of something? Let's say e to the power of x squared plus 1. What is its derivative? Well, it is e to the something, right? So then we first take the derivative of e with respect to this variable. Then we get, so let me first write it down slowly, and then we'll be more familiar. This is, because the derivative of e to the something is e to the is itself. So this is again e to the star. Again, we need to multiply by the derivative of the star. So in this case, let me erase this. This is equal to, we think about this as a variable, and then take the derivative. Then we get it's e to the x squared plus 1 again, because exponential has the same, the derivative of e to the x is also e to the x. And then we need to multiply by the derivative of x squared plus 1, which is 2x. So this is 2x times e to the x squared plus 1. So now, let me tell you the formula of the chain rule. So chain rule says that if you want to look at the derivative of g composed with f at x, then this is g prime at f of x times f prime of x. So that's exactly the same meaning. You think about this f of x as a variable, and then you take the derivative of g with respect to that variable. Okay? And then you need to multiply the derivative of f. And if you cannot do it in one step, then you need to do it in several steps. So for example, if you have h composed with g composed with f, and then the derivative should be equal to h prime of this entire variable, which is g of f of x. And then you need to multiply the what's remain. So you need to multiply by this. But also again by chain rule, this is equal to g prime. So now you think of f of x as the variable. So then you take the derivative of g and then evaluate it at f of x. And then this f of x, you need to take the derivative of f, right? So it's in this way. So in general, if you have let's say n functions, f1 up to fn, then it's going to be f1 prime of all the other, f2 all the way up to x, times f2 prime of f3 of all the way, and then times all the way up to the second last term, which is fn minus 1 prime of fn of x multiplied by fn prime of x. Okay, so let me show you some examples. So what about e? So let's say sine of e to the x squared plus 1. What is its derivative? So first, it is sine of something, so it should be cos of this guy. So we just think about this as a variable. So cos of this guy times the derivative of that, right? And then this is again e to the something. So then this is e to the, and then the derivative of e is again e itself. So this is multiplied by e to the x squared plus 1. And then we need to take the derivative of that, which is 2x. And then if you want, you can simplify. But that's the pattern, okay? So you can do it in one step. So let me show you how to do it in one step. So if you want to look at the derivative of sine of e to the x squared plus 1, then this is the first big variable. You take the derivative, it becomes cos of this variable. And then you look at this variable. You want to take the derivative of exponential, but it's itself. So it's e to this smaller variable. And then you take the derivative of this small variable. And you can do that. So you're done, times 2x, okay? So this is how you will use the chain rule. So for example, you can use it to find what is the derivative of a to the x for any given a beginning 0 and a not equal to 1. So what is this? So this is a general exponential function. So because we can write a to the x as, because a is equal to e to the ln a, right? This is by one of the formula in the logarithmic rules, right? And then you need to multiply, you need to raise it to the power of x. So this is going to be e to the ln a multiplied by x, or if you wish, e to the x times ln a. It doesn't matter. The point is that it is e to the some multiple times x. And then how to take its derivative? Well, the derivative of a to the x, you can use chain rule to deduce that this is the derivative of e to the ln a times x. And then this is e to the something, so the derivative is also e to the something, so it's e to the ln a x. And by the way, this is, again, you can go back, this is a to the x. And now here you need to multiply the derivative of this with respect to x. And this is a linear function of x whose slope is everywhere ln a, so you're down. Or you can think about this ln a x, or in general, the derivative of kx, where k is a constant. This is k times x prime. Well, x prime must be 1, so this is k, okay? So here it's just, you need to multiply by ln a, which means the result is a to the x ln a. Okay, so this is also one of the important formula. So the derivative of a to the a to the x is a to the x ln a. Very important. And similarly, you also have another formula. So it's about log a of x, where again a is bigger than 0 and a is not equal to 1. So what about the derivative of this? So again, by some you can change the base of the log, and then this will become, and you make them to be both ln. So this would be going to be ln x over ln a, right? Because in general, log ab is going to be log, you can just choose some random c that is bigger than 0 and not 1. So this will become log cb divided by log ca. So here you just choose this to be e. So then this becomes the ln, okay? So then log ab is ln b over ln a, okay? So here it's ln ax. Here it's log ax. So this is ln x over ln a. But here it's very easy actually, because this is simply a constant 1 over ln a multiplied by ln x. This is a constant, so this is 1 over ln a multiplied by the derivative of ln x. And we know that the derivative of ln x is 1 over x. So this is 1 over ln a times 1 over x, which is 1 over x ln a. Okay, we can just put all these formulas together, and then we get the derivative of e to the x is e to the x. The derivative of a to the x is a to the x ln a. The derivative of ln x is 1 over x. The derivative of log ax is 1 over x ln a. Okay. So you can see just all the ln a just come together with what it should be belong to. So ln a comes with the x. So you can just remember this form. And if you forgot the formula, you can just use chain rule to do it again. It's very easy. Okay. So maybe we can do some exercises. So maybe we can look at what's the derivative of e to the f of x in general. Then it's e to the something, so the derivative is also e to something multiplied by f prime of x. So in general, this is f prime of x times e to the f of x, right? For example, e to the sine of x, e to the 2 times sine x, right? This is going to be the derivative of this, which is 2 times cos of x times e to the 2 times sine of x, okay? What about f of 2x, for example? What's the derivative of f of 2x? Then you look at the derivative of f at this value, which is 2x. And then you take the derivative of 2x with respect to x. So then you get 2. So this is 2 times f prime of 2x. So in general, the derivative of f of kx is equal to k times f prime of kx. So one example is that, what's the derivative of sine of 3x? Then this is 3 times cos of 3x, okay? Because you can first do it with cos of 3x, and then you can multiply by 3. But if you know that this is in the form of kx, then you win, right? You can just directly put this 3 over here. And in general, you can just make it into kx plus b, where b is a constant. Then the derivative of kx plus b with respect to x is also k. So this becomes k times f prime of kx plus b. Okay? So maybe you can do, for example, sine of 3x plus 1, let's say. Then the derivative should be 3 times cos of 3x plus 1. You just play with it, okay? It's not hard at all. And then you can, for example, also look at the derivative of ln of f of x if it's well-defined. So which means if f is always positive, then this derivative is going to be, you look at this ln, so the derivative of ln is 1 over that. So this is 1 over f of x, but still you need to multiply by its derivative, which is f prime of x. And this is very, very important. This is called log differentiation. So by log differentiation, what you get is its derivative divided by itself. It's extremely important afterwards, okay? It's extremely important. I think it's the most important formula in calculus that you will understand later. But for now, maybe just this is not so important. But later it will be important, especially, for example, in complex analysis and analytic number theory. Okay. So by the way, you can use this to reprove the product rule. Okay. You can use this to prove the product rule. So let's do it. So which means we want to show that the derivative of fg is equal to f prime g plus fg prime. Okay. But how do we show it? Well, we can look at the ln of f of g. Then this is going to be ln of f plus ln of g by one of the rule of log. And then we can take the derivative of both sides with respect to x for sure. Take derivative with respect to x. Then on the left hand side, what we get is, so we can think of fg as a function, right? It's a function. So then by the log differentiation, the log f prime is f prime divided by f. So here, this gives you fg prime divided by fg, right? Because fg is also a function. It's log of, so we can call it h, log of h. Then we get this, right? We can plug in. We can use log differentiation rule to get this. And then again, for this time, this is f prime over f plus g prime over g. Now, what you can do, I mean, you're asked to find the derivative of fg, and here you are. So then you can get fg prime is going to be fg times f prime over f plus g prime over g. So then you can multiply them in. So then you get f prime g plus fg prime, and then you realize that this is true. Now we can actually, without using proof by induction, we can prove directly the generalized version of the product rule, which is the derivative of the product of n terms. So let's take a look. So what about so let's show, maybe we can just find the derivative of f1 up to fn. Then we again use the trick of log differentiation. We know the log of the product of n terms is going to be ln f1 plus all the way up to ln fn. And then we take the derivative with respect to x on both sides. Then on the left, we get the derivative of f1 up to fn divided by f1 up to fn is equal to f1 prime over f1 plus all the way up to fn prime over fn, which means the derivative of f1 up to fn is equal to f1 up to fn multiplied by f1 prime over f1 all the way up to fn prime fn. So we can just look at one term. For example, in the first term, so we should have f1 up to fn, but then we cancel out, we delete f1, and then we add f1 prime, which means you can just think about this as we add a prime over here, right? So like in the last term, we delete fn, and then we add fn prime. So you can think about it as we add this prime over here. So each term is that we add a prime somewhere. So then what we get is what we want, right? So by using this trick of log differentiation, you prove it without pain that this is equal to f1 prime times f2 all the way up to fn plus f1 times f2 prime f3 all the way up to fn, and then the last term is f1 up to fn minus 1 and then times fn prime. And then using the same trick, you can actually deduce a stronger formula, which is, so for example, you can prove in the same way the quotient rule. Okay, so let's prove the quotient rule. we can just play with it. Okay, so let's prove the quotient rule again. So what about the ln of f over g? This is going to be ln f minus ln g, right? So then we take the derivative with respect to x. We get the derivative of f over g divided by f over g is going to be f prime over f minus g prime over g, which means this will be the derivative of f over g, which is what we want to find, which is what we want to find is going to be f over g multiplied by f prime over f minus g prime over g. So if you want to calculate, then you can cancel out this f in this term. So the first term becomes f prime over g. The second term is f g prime over g squared. So that this becomes, if you want the denominator to be g squared, then this is f prime g minus f g prime. And you can see you don't have this. You cannot simplify this when you have more terms, right? Because here you will have some complicated versions. But the point is that the essence of this is really the log differentiation. Because let me show you a much more generalized version. So let's find the derivative of f1 times all the way up to fm divided by g1 all the way up to gn, where m and n are not necessarily equal. So let's find its derivative. So again, we can apply the log of both sides. So then this will be going to be the sum of log f1 plus all the way up to log fm minus the sum of from log g1 all the way up to log gn. And then we apply the derivative to both sides. Then on the left we get this guy derivative divided by that, and then we can just move it to the right, okay, just to simplify the calculation. So this is going to be equal to f1 all the way to fm divided by g1 over gn, multiply by f1 prime over f1 plus all the way up to fm prime over fm, and then this entire thing minus g1 prime over g1 all the way up to gn prime over gn. So this is the final version of the product or quotient rule. Okay, so you can use it to find whatever you want, if it's in the terms of product or quotient. And if you have some addition or subtraction, then you just use the simple rule: f plus or minus g prime is f prime plus or minus g prime. Then this will be easy. Okay, I think that would be enough.